Alright, so today I'm going to be explaining another important paper with the title From Local to Global, Spectral Inspired Graph Neural Networks. This NeurIPS paper in 2022 is very important. Graph neural networks are powerful deep learning methods for non-Euclidean data, and however, shallow message passing neural networks tend to miss long-range signals and perform poorly on some heterophilous graphs, while deep message neural network can suffer from issues like over-smoothing or over-squashing. To mitigate such issues, existing work typically borrow normalization techniques from the training neural network on Euclidean data or modify the graph structures. Yet these approaches are not well understood theoretically and could increase the overall computational complexity. So we draw inspiration from spectral graph embedding and propose power embed, a simple layer-wise normalization technique to boost these message-passing neural networks. We show power embed can provably express top K leading eigenvectors of the graph operator, which prevents over-smoothing and is agnostic to graph topology. Meanwhile, it produces a list of representations ranging from local features to global signals, which avoids over-squashing. So the task is to find a permutation equivariant function f for all permutation matrices while preserving the graph structure. Similar nodes should be close to each other in the embedding space. And spectral embedding choose f based on matrix factorization. For example, f could output the top k eigenvectors of A. Message-passing neural networks seem to perform poorly on several heterophilous graphs. So to evaluate the graph embedding H, this graph embedding, we consider the node classification task. Given a graph G of n nodes, the goal is to predict the remaining n minus n sub t test labels. And omega and omega perpendicular, where the indices correspond to training nodes and test nodes respectively. Then the classifier is trained on the training set and evaluated on the test set. If the graph embedding is a list of features, then we set them, the training set and the test features. So this is P sub omega is the training set features. And these are graph embeddings. A graph A with n nodes is a random stochastic block model if it is sampled like this from this Bernoulli distribution. Another definition is a two-block symmetric stochastic block model is given by this, and this stochastic block model is a canonical random graph model with planted clusters which have been widely studied. And it's a canonical with and in particular, the leading eigenvectors of the graph adjacency A provably encode community membership provided the graph are sufficiently dense. Now, in this work, we consider classical spectral embedding methods, and we let A to be USU transpose and XX transpose to be this SVD decomposition. Spectral methods that are based on top K eigenvectors ranked by absolute magnitude have no assumption on the graph being homophilous or heterophilous. They perform consistently well on both cases by looking globally at the graph structure. In contrast, message passing methods are local algorithms that work well in homophilous graphs, but they tend to overlook global signals and struggle to learn in heterophilous graphs. So this is a layer message passing neural networks. For example, graph convolutional narrator chooses phi as a nonlinear activation, and so GCN can be further simplified by removing the nonlinearity sigma. And we have these over-smoothing and over-squashing problem. So the algorithm requires a graph operator S, node features X, and a list. So we go through this message passing, we do normalization, and it returns P, which is unlike existing work that requires pre-computed eigenvectors as input, our approach implicitly computes eigenvectors using power iteration to improve efficiency while maintaining expressivity. So this produces a list of embeddings ranging from local neighbor average features to global spectral information, which is then jointly learned by using an inception neural network. And this inception was first used in computer vision, but now you can use it in many different tasks. So we concatenate after this inception network, this MLP, we concatenate all of them, node features, local features, and the global features, and then we give it to the classifier. That's the idea, how we do node classification with inception networks. And by the way, this Squirrler and Chamilson are these two are very difficult because they are not homophilous graphs, they are heterophilous graphs, and that's why your results are very even state of the art is less than 60%. Cora, so its site 0 are very simple.